Let's do an electromagnetic wave. What is that? Anybody? Give me a basis for where your perspective is about what you think an electromagnetic wave is.
I read
Anybody?
that was like light energy.
Okay, good. Yeah. So what is light?
So, um,
In fact, I would say that just to kind of sharpen your answer, an electromagnetic wave is light, and energy is something that it has. So there is energy in light or energy in an electromagnetic wave, and that's one way to describe it. But I guess what I was really looking at is what you said is that the connection that when we say light, that's light is an electromagnetic wave. So that's basically what I was looking for. Uh, so good. But I also want to emphasize the point that when we say light, normally we're speaking of visual light, like when we turn on a flashlight or the light coming from the sun. But in general, light is any electromagnetic wave, technically. So, like, and also maybe you don't know that, maybe you do, that an electromagnetic wave, like visible light, it's basically the same stuff that's the other electromagnetic wave, like your microwave oven. Essentially, visible light and microwave microwaves in your microwave oven is the same stuff. It's just a different frequency and wavelength. That's how you distinguish between different types of light. Frequency and wavelength. So there are different types of waves that we study in nature. There are mechanical waves. And a mechanical wave is like the wave that you see a mechanical wave is something that is traveling on a physical medium, like water or string or air. Well, air, technically it's sound. It is mechanical, but we have a specific name for it called sound. When I'm talking right now, or with music, what happens is, well, like with my guitar string, you get a vibration. All waves come from some sort of vibration. It starts from that. So, like a sound wave is a kind of mechanical wave, but we just call it sound. That's the name that we use. So, with the guitar, the thing that starts to vibrate is the string. It vibrates at a certain frequency and wavelength. I'll describe it in a minute. And that vibrates the air. And so it sends the wave out on the air, a longitudinal wave, and it comes to a sensor like your eardrum. It makes your eardrum vibrate, and your nervous system converts that vibration to an electric signal that goes to your brain and corresponds to the specific frequency of sound that you hear. Visible light works the same way. When you see a rainbow, that's starting from in the sun or wherever, there is the wave starts coming from the sun from an oscillating charged particle in the sun. And that's how a wave is, how it starts. It's a charged particle that is spinning, that has both a magnetic field and an electric field. And when that thing oscillates, it sends the wave out in space. And it has a specific frequency and wavelength, and that when you're under certain conditions, like when the white light is separated into, like with a rainbow, again, the way your eyes have certain sensitivity to the colors that correspond to the frequencies that correspond to the different colors you see, and that's why you see different colors. So it's a symmetry there with all different waves. You have to be able to sense the frequency and the wavelength of that specific wave, and that's how the waves are distinguished between certain characteristics like color in the case of visible light, or sound in the case of visual. There are some frequencies and wavelengths that we can't sense, like the other waves in the other light waves, and the other types of electromagnetic waves that I was alluding to, like a microwave. We don't have anything in our physicality that can sense that, but we can create things, sensors that do. Microwave is a good example. Another example is the waves that we're using right now to communicate. So those are radio waves. Your cell phone uses the same type of range of frequency and wavelength as the radio in your car, and those are radio waves. Most of the ways that we deal with in terms of, you know, remote control devices, like this is for my air conditioner or for your keys or anything, most of those are radio waves. In fact, all of them are, I believe. The same type of radio waves that we send when you're using, radio waves like for your car. So frequency and wavelength. So I was going to kind of describe it, and you've probably seen this to some degree before. Like if I have a string, well, like that exercise that people do in the gym now with those big long ropes, right? They get the rope. That's the example of mechanical wave. And what's actually happening, and again, I think go with Thomas's answer. Obviously, the string, it's the rope itself is not translating. When I'm saying translating, I mean like right now I'm translating myself across the room. I'm physically moving, and I'm my position is changing, my overall position. The interesting about a wave is that a mechanical wave is the rope clearly is not moving, right? Because the rope is connected between the person's hand, that's a node, and wherever it's connected on the wall or wherever. So as he does that motion, the whole rope doesn't move across the room, right? So it's not moving at all. It's not translating at all. Excuse me. It's not translating at all. What it is doing is waving. And what that means is he's moving or she's moving it in such a way that energy is actually moving along the string itself. And that's essentially what a wave is. It's the propagation of energy along a medium in the case of mechanical wave. And it does that in this oscillating fashion, right? So a wave, mechanical wave, will distinguish um, is the propagation, means movement, of energy along a a physical medium like a rope or water, water, air, or rope, or anything, even like well, like the earth. In a hurricane, like when you drop a pebble in water and it sends out those spherical waves. Many people may not realize that that actually is how an earthquake's waves travel along the earth. If you could see it from the earth, from the top down, wherever the epicenter of the earthquake is, the earth actually would look like water. It's wavy as the wave propagates away from the center of the earthquake. And some people have actually even noted in when they've been in earthquakes, like if they're on high ground over a valley or something, and they can see the earthquake coming, the earth rolling. And it depends really on the frequency and wavelength if you can see it really well. For many of the earthquakes, the tremors that we have, the wave is so small it just shakes things. You can't really feel it or feel the wave. But for it depends on the it's not really the magnitude. It depends on I think how quick the initial disturbance is, how quick or slow the initial disturbance is, as to what the frequency is and whether or not you would be able to see that kind of rolling nature in some way. But it basically propagates as a spherical wave, and it makes the Earth look like it's water. Like if you could see that it has that type of basically it's the same thing, same way as how a wave would look propagating in water. Um, so yeah, so a mechanical wave is a propagation of energy along a physical medium, like rope, like air or water, in an oscillatory fashion. And a really great analogy, as I said, is the that exercise that people do in the gym. Um, so waves are characterized by certain quantities that I've been saying, frequency and wavelength. And so if I were to kind of have a graphical representation of a wave, and what I like to do is to visualize like a string. That's a string is a really nice physical visualization of what's actually how we would represent a wave mathematically. And again, think of that example that I just gave. If I had a string and I attached it here on the wall, on if this were physically a string and I attached it at the origin of my coordinate system, I might make the thing look something like. Actually, let's do it so that the if when undisturbed, the string was flush along the x-axis. Actually, no, let's just yeah, sure, let's do that. I'd be able to represent something like that. Okay, so we can specify specific parameters associated with this representation. So trough to trough distance is called the wavelength. Trough to trough or crest to crest. Different symbols we use to represent wavelength. I don't know what your book is using. I'll just I'm going to use a Greek symbol called a lambda. That's just something that we conventionally use to represent wavelength. So here I'll say wavelength, lambda, and that's pronounced LAMDA. And it's the crest to crest distance or trough to trough distance, which is the same thing. So crest to crest here, trough to trough is this distance here, and it's the same distance. So or trough to trough. The maximum displacement of the wave from its equilibrium position. So if this is along the y-axis, and I guess you could just visualize this literally as if I had a string here and then I whipped it like, this is not going to really do it very well because it doesn't have a lot of elasticity. But just imagine if I literally attached a string at this point in my origin and I came over here and I whipped it like that, just like the thing in the gym, it would take on a shape like that. We call it a sinusoidal shape. So we characterize physical properties of a wave in the way that I'm showing you here. So the amplitude, if this is the normal equilibrium position, like if I just had the string, with undisturbed, it would, as I said, be attached along the x-axis. So when I disturb it, though, physical parts of the string will then move away from the up or down from the equilibrium position, which is essentially zero along the y-axis. And so the maximum displacement in one direction would be the amplitude along that direction, and vice versa in the other direction. So and usually we have symmetry associated, at least the way we set it up with with a situation like that. So this would uh, denote the amplitude in the positive amplitude in terms of displacement. So let's say that the distance of the amplitude is a, so that this would be positive a, the distance that it displaces from equilibrium in the positive direction, and this would be negative a. So the amplitude is the maximum, what we say, displacement of the physical medium from its equilibrium position. Displacement or disturbance. Okay. Um, and we can also describe, so as I mentioned that there's an oscillatory fashion. Oscillatory, what does that mean? Oscillatory is anything that repeats itself in a cycle. So the Earth rotating on its axis is oscillatory. The Earth rotating around the sun is oscillatory. The moon around the Earth is oscillatory. The moon around its axis. Anything rotating around its own axis is oscillatory. A great example of oscillatory motion the is my oscillating fan in my roof. So I think I can turn this camera around. You see that? See my fan there? That anything that does something like that is oscillatory. Is the one of the physics terms that we use to describe that kind of motion, as opposed to other kinds of motion, which I just mentioned early in class. Translational motion is motion that's characteristic that it moves along a line, usually without changing direction or the oscillatory motion has the characteristics of those examples that I just mentioned, the fan included. So, in in a way, though a wave combines both. It combines translational motion and oscillatory motion. Um, Translation of the energy and oscillation of the medium. So the medium actually is oscillating. The physical string is oscillating. It's not translating. The energy is translating and not oscillating. And going back to what you said, I really like your answer, Thomas. This is the third time I've come back to it. You kind of incorporated that in your answer because you said something about light with energy. We'll talk about there's some differences between an electromagnetic wave and a mechanical wave, which is what I'm describing here. But the first basis of understanding, usually in physics, when we're presenting this to material to students or people who kind of maybe understanding for the first time, or is we usually start, and in general, it's always good to do that, start with something that is much more practical that you've experienced physically with more of your senses in a way that you're aware of. And any kind of mechanical way, we've pretty much done that in some way. And so that's what I'm starting and kind of describing these basic parameters using a mechanical wave. So the point that I wanted to make when showing you the oscillatory motion is that we can describe something called frequency and period with respect to the type of the, in the case of rotation, the rotational motion or any oscillatory motion. And period is the total amount of time it takes for something to go through one cycle. And there's usually four stages of one cycle. Four stages meaning I could describe another type of cyclical motion with a simple pendulum like this. And if I think of a cycle as up and back, so if it starts here, in fact, you can start it anywhere. But if I start here, up and back is one cycle. You have to go. The object, the physical object, has to be back in the same position that it started, moving in the same direction, and that completes one cycle. So, for example, if I started here in the middle, assuming that the motion is looking like that, right, is oscillatory motion in that nature. If I took a snapshot and started right here, I'm in the middle, but I'm in the middle going to your right. Well, I go up, that's a quarter cycle. I come back, that's a half cycle starting over there. Now you see I'm in the middle position again, but I'm going in the opposite direction. So that's not a cycle. In fact, that's always going to be half a cycle. A third quarter of a cycle is going up to the other amplitude, and then now coming back in the same direction so I'm now back in the middle, going in the same direction as when I started counting. That completes a cycle. And I can break that cycle up into 4 quarters. That's usually always the case, regardless of how the oscillatory motion is being experienced or manifesting with a particular phenomenon. So we can define period. Period is the time to complete one cycle. Any type of oscillatory motion, whether it's a simple pendulum like the one I was just demonstrating, whether it's a fan turning around or a wave on a string. In other words, a point on this string, if you could do it in real time, if I started here, that point will be moving down, right? If you look at a point on a string, even though the energy is translated, and it looks like something is translated, it's energy, right? The actual physical string is actually just moving up and down in oscillatory motion. That's what I mean, that the medium itself experiences oscillatory motion, but the energy that's moving along that wave experiences translational motion. We can break down those two different things and talk about them as describe what the energy looks like, how it's moving. Again, we won't do that in this class, but in a higher physics class, that's what you do. You have mathematical equations that describe how the energy is moving, what it is, and how the actual medium is moving, and how they're related to one another. It's called wave mechanics. So period then is the time to complete to complete one cycle of any kind of oscillatory motion. So I just said time to complete one cycle. The symbol that we usually use for whatever reason is a capital T, and I usually put little hats on my T to distinguish because there's other things we use capital T for, like tension. Yeah. And another quantity that's very much related to that is frequency. That's something that you're also familiar with. Frequency, even though you might not know it. Frequency is the number of cycles per unit time. That is the number of times it goes around in a unit of time. The unit of time in physics, the standard unit of time is the second. And so if you have something that's oscillatory, you count how many times that rotates in a second, and that is the frequency. So number of cycles per unit time. And the symbol for frequency is like a script F, a little F like that. So the relationship between period and frequency is that one is the inverse of the other. So period is equal to the inverse of frequency. Can anyone give me an example of frequency where we use frequency in a very kind of everyday experience and that everyone is probably familiar with this example of how frequency describes something that we consider very useful in our society and that we use all the time? Where's an example where we use the term frequency and we use it to rate something that most people consider pretty valuable and most people possess. In fact, all of you are using one right now, or some version of it.
Electronic devices?
Yeah, but a specific electronic device, Dahlia. Which one?
Laptop?
Yeah, and so how does frequency, what is the specific parameter that I'm referring to with regard to a laptop?
Are we are we talking about Hertz, Wi-Fi, sound waves?
Yeah, we're talking about like hertz, like what when in a computer, usually you rate how valuable the computer, how powerful the computer is by something called gigahertz, right?
Yes,
What is that? Go ahead.
I think if I pull it up, I think my laptop is once 44 gigahertz, I think.
144 gigahertz. So what is that describing about your computer? Do you know?
No, I'm sorry, I really don't.
Okay, let me help you. First of all, I said seconds, that the unit of time for period is seconds. So the period, its unit is seconds actually. So, like if I were looking at how long it takes my fan to move around, it looks like it's about half a second, maybe even a quarter of a second. So the units for a period is seconds. Now, when I write units, I usually use brackets. So this would mean the units per period, is a second. I probably would just write it like that. Now, frequency is 1/2 So technically, the unit for frequency, if I wanted to write it in terms of the actual parameter, it's like some units have names. So I could say that the units for frequency is 1/2, where second is a symbol. But sometimes we give units a name after the scientist who was, you know, instrumental in understanding the concept. So, for example, the unit of force is a Newton. Well, we can still break it down into basic measurement units. A Newton is a kilogram meter per second squared. But because of respect, because of convention, we decided to give the thing a name because Newton was so great. We do that with frequency. We don't do it with period, but we do it with frequency. The name of the German physicist who I think defined this in the first place is, I forget his first name, but his last name is Hertz, just like Hertz, like the car. And that's where that comes from. So it's a proper name, Hertz. I think he was either German or Swiss. So the unit then for frequency is 1/2, but we call it hertz. It's the guy's name. The abbreviation for it, so its name is spelled just like the car company, but the abbreviation is HZ, I think, capital HZ. So I'll put that something. Yeah, I don't know. I'm running out of space. Yeah, I'll do it here. So again, unit of 1/2 is a hertz, which can be abbreviated HZ. Now, with processors, I used to think back in the day with the old school Appletop, they had actually uh, physical processors inside that spun around. I used to think that it was the rating was how many times the thing spun around, per second. But then I realized that can't because you got like 144 gigahertz. That means that whatever the operation is, it's doing it in such a fashion that it's performing 144. Now, giga is 10 to the 12th, I believe. That's 144 times 10 to the 12th processes per second. So it clearly is nothing mechanical spinning. What it is saying is that when a computer performs a computer program, it's actually performing certain processes in computer science language. Maybe there's a few programmers in the class. You can explain this a little better than I can. But the power of the computer is basically the solid state software is made in such a way, the actual material, in such a way that electrical processes can be performed on the material. And the limitation is the material of the solid state material that the circuitry is made of. As we get material that is basically more powerful, where we can perform more operations on it, and that basically has to do with physical properties of literally the compounds of the material that you're putting together, we're able to make more powerful devices. More powerful means that you can perform more operations per unit time. So what that processing speed is not really a speed, it's a frequency, as I just mentioned. It's telling you literally how many operations your solid state material can physically perform per unit time. And the more operations, obviously, the more powerful we say the computer because it can do more in less time. And it also usually is smaller because as we get more powerful and get more advanced, not only do we can make the material, more powerful in that sense, we can usually do it in such a way that because the material itself is more powerful, we don't need as much to make a particular type of circuit or to make a device. And so that's why there's this trend that not only does as technology advances, it also usually gets smaller. That's why. Um, so that's for now. So that's what processing speed. That's what that is telling you. Because with computers, it's cyclical, right? You just have ones and zeros as usually performing operations over and over again. So it's kind of making an analogy between the the process of the computer performing the code. It's making an analogy between that and some sort of oscillatory system because it's doing that over and over again. It's not nothing is actually rotating in the software. It's an analogy, but it's a good analogy. And actually, for older computers, there were things that rotated. The mechanical stuff, the processor was a mechanical processor, and it did rotate. So the terminology started there, but now it's all solid state stuff. So we don't have it's less and less mechanical things, but we still use that same terminology for what's happening inside the software and inside the physical material. So the that's where this is coming from, and we still use that terminology that the number of processes that the computer can perform per unit time is what we define as a frequency. And you can see like gigahertz. I mean, giga is I say is 10 to the 12. So 144 gigahertz. I think that's what you said. This would be the way you would write that symbol, and that's what you see when you look on the ratings on your computer or whatever. Or, any of these things, watches all anything that goes by computer program or software is going to be rated in that way because it has to have a processor. But that's the same thing as 144 times 10 to the 12th. And that's going to be operations, usually a symbol like number per second. So that's how many times how many operations computer operations or code operation that's happening per second for that software. Yeah. So that's waves in general. Those are the basic parameters. There's a couple other things we could say, but that's basically it. The kind of an introduction to wave mechanics. Now, this chapter is not about mechanical waves. This chapter is about electromagnetic waves. Now, how is that different? Well, first of all, let me backtrack and talk about the 7 types of electromagnetic waves that we can see. There are 7, and they list them in the book. I'm just going to list them here. Electromagnetic waves, they're not mechanical because what we say in physics is that, well, we used to believe that space was a vacuum. This actually is not true anymore. And as I've told you about how physics evolves. When I was an undergrad, the going terminology was that space is a vacuum. There's nothing in it. So if there's nothing in it, and an electromagnetic wave can travel from the sun to the earth, it must not need anything to travel on because there's nothing in space. So, and they still have this terminology in books. The conventional thing is that an electromagnetic wave doesn't need any medium to travel on. I never really bought that because it didn't really make sense to me. But now, quantum mechanics and things are kind of suggesting that there actually is a medium. Won't get into that so much, but I just want to kind of tell you that we're kind of in a transition right now, but that really hasn't reached books. So I don't think it's fully correct anymore to teach that electromagnetic waves do not have a medium. However, that is the conventional teaching. And so what is it? Well, it's just an electric field and a magnetic field oscillating together and moving through space. That's what an electromagnetic wave is. Now, to give you some background to help you with that a little bit more, um, and this is where my kind of the conventional teaching ends, because this analogy is going to kind of bring up something that is not really the way this is normally taught, but is very useful because I think it helps to understand what an electromagnetic wave actually is, and thus what light is. Let's take a charged particle. Now I know that we haven't dealt so much with that, but there is, you know, there are electrons, protons. You've probably heard of these things. These are the building blocks of nature. If I were to take my fingernail and, if I could scan in large enough or, close enough, I'd be able to see basically a lattice of atoms. I don't believe I introduced the Einstein model here, but Einstein back in 1905 or something introduced the first concept of what material looks like on the inside. And it's pretty simple. I'll just say it here, Einstein model. I'm so frustrated with this thing. They're gonna need to get new markers. The black ones don't keep the ink anymore. I don't know why. Sorry about this. So sit there for a minute. Actually, I don't think I need to do the Einstein model to illustrate this. So let me, oops. When we represent a charged particle, we represent in the following fashion. So let's say that I have a positive charge, like a proton. We say that the proton has a field around it. And the field, if you could see it, these lines would represent something about how it's behaving. The field points radially away from the charge and does something like that. Like that's a positive charge. A negative charge would have lines that are doing the opposite, that would go inside. In fact, a negative charge is kind of like gravity. You could represent a gravitational field in the same way. So here's a negative charge, and the field lines for a negative charge go in radially like that, pointing in toward the center of the of the uh, of the charge. If it were the Earth, so there's certain types of fields that we deal with on our everyday lives, and there's not that many. There's only a couple. There's gravity, a gravitational field, the concept of a field. Gravity. There's an electric field, electric fields, which we deal with electricity, and there's magnetic fields. These happen to be called conservative fields, but we won't go there yet. We'll go there. We'll just say that these are fields. All fields have forces associated with it. So we can't really directly experience the field. We can, but we don't really realize it when we're doing it. But we can definitely feel the force associated with that field. So with gravity, the force associated with the gravitational field makes us fall toward the Earth. For a positive charge, positive is kind of repulsive, and negative fields for electricity is attractive, and they attract one another. In fact, you get to say, well, basic and negative can be positive. It turns out that if you have two charges that are positive close to one another, they repel one another. Or two charges that are negative, they repel one another. But if you have a positive and a negative, they attract. So it's a little bit more complicated than what I initially said. But you're familiar with that because you know that if I were to rub a piece of glass, I think maybe I didn't, but I can show you what static electricity most things are neutral, but if I rub glass hard enough, I can rub off charged particles, uh, electrons onto the glass from like something that has a lot of them, like wool or something like that. And I can I can pick up paper with it because it will attract the charged particles basically in the paper. And that's where I was going to show the Einstein model to kind of show what's happening on the inside, but we'll do that later. I think that's a couple of chapters later. Right now, I just want to kind of describe it briefly to talk about the fact that there is this thing called field. And yeah, and so I could do that here and to show that, in fact, there is a force associated with the electric field, and therefore that gives evidence that there is something called an electric field. We could do something similar with two magnets, right? With magnetic, these magnets are pretty strong here, so it's hard for me to pull them off. But like a magnet has a field, two magnets that have opposite polarity work somewhat like two charges with opposite polarity, right? There's a field here, and the field is actually extending from these magnets, even though I can't see it. But as I said, you can't really interact with field. It's hard to understand that a field is there, but in certain conditions, that the force associated with that field can let you know that the field is there because the force acts on certain things. So all these fields have the same kind of characteristic, right? The field is right here, like the field is right here in space, but I can't see it. But if I put something there in space, there's going to be a force on that thing, and it's going to cause that force is going to cause that object to react. So the field is always there. The force is only there if I place an object there that the field can interact with. All of these things have that same type of characteristic. Okay, now let's say that we have that field. And again, if I were to show the field of the Earth, right? This is the Earth. The gravitational field looks somewhat like the electric field associated with a negative charge. It points in toward the Earth, which is why when you're on the surface of the Earth and you drop something, it makes it look like it's falling down because it's falling toward the center of the Earth. So right now, these field lines, I represent them with G. I represent both of these with E because they're electric fields associated with these guys. Right now, there are G field lines that are pointing toward the center of the Earth that I can't see. But again, as I said, if I put an object in anywhere in that vicinity of that field, then that field will have a force on the object and cause the object to move. So the field is it's around us. So I want you to visualize. We can understand. I think we have an intuition for that because we know what gravity is. But I want you to intuit that the fields associated with these charged particles, they are the same. And I don't want to spend the time. I could go and get some paper and put it into a glass and show you that I could pull up paper just like, and the field, the electric field can have a force on paper just like the gravitational field is having a force on this pen. I could do that. I'll do that at some point, but I think you probably believe me. Just take my word for it. At some point, I can show you that explicitly. But I think you know that happens. You can see it whenever when you're in your dryer, right? And because of the motion of the dryer and the heat, it causes charged particles to rub off of in the atomic structure of things like wool and cotton, and deposits electrons on this other material. So when you pull it out, that's what the static electricity is. The electrons have gotten rubbed out of their bonds in the material, and they're just sitting, even though you can't see them, they're just sitting on the material. So they charge it, right? And so that's when you pull it out, it can stick to you, and so that's what's happening. You've got these non-neutral fields now because the electrons have been displaced, and it's temporarily charged these pieces of clothing. The reason that the charge goes away is because water molecules in the air, and the water molecules are like right? Water is H2O. I think you might know that. But the molecule is very distinct. If you could see it, it looks like this. We have this big oxygen molecule, like that. So that's oxygen. And then you have these hydrogen molecules here that are small. And this is literally what the oxygen molecule looks like. It's like an anvil, has its own frequency, it vibrates. You can see it. These things are positively charged, and this thing is as two negative charges. The I don't know. I'll just put -2, the oxygen. But so the overall molecule is neutral, but it's in such a way that each of these are kind of like prongs. So this thing, a water molecule, they're floating all in the air right now. Now, if I could take, and you know that static electricity is really strong, right? Because you could take like static electricity of one of your socks and pick up the other sock, like from two inches or something. You know that's how strong a static electricity can get. Now, if the electrons on one sock can pick up another sock, which is probably like 20, 30 grams, a water molecule is probably like 0.00003 grams or something like that. I don't know. I guess I don't even know how you would measure it. So if static electricity of one of your socks can actually pick up a sock, the static electricity on that sock can draw water molecules from meters across the room. And it does over time. And eventually there's enough water molecules that it draws to it that it neutralizes the charged particles on the sock. And that's why over time the static electricity dissipates. Because water, like these charged, like it's, the electrons are negative, right? So these these molecules that are just floating in the air, the hydrogen portion of the molecule will kind of feel the electric pull of the field on the sock and pull it toward it and then just stick to it. And then the positive and negative will neutralize. And over time, all the water molecules will neutralize all of the charged particles that have been displaced and cause static electricity on the sock. So that's an example that these things are real. Fields are real. And the basic ones that have been here since the Big Bang in our universe are gravity, electricity, and magnetism. Those are the only fields that we know. I think there might be one other, a couple other, at least one other out there. I don't know. That's just me. But conventional science teaches that. Now, that's what a field is. Now, if you can just get a little bit of electrons, in a dryer that get displaced and knocked off, the materials and can charge things, just think about all the energy that's going on in the sun. Not only do you kind of strip electrons away from their atoms, you actually strip the whole thing, like the whole thing is just stripped apart. The thing meaning whatever the element is, whatever it is, like it completely disintegrates it. And just that's actually a really good analogy. If you think about the heat and the turmoil going on inside your dryer, I don't know, you just take that and multiply it by a gazillion, and that's what's going on in the sun. So you've got all of these displaced charged particles in the sun, right? Doing their thing, doing the fusion thing. Actually, it's like a fusion reactor. But the point is, you definitely have charged particles with their own fields, separate fields, and they're just moving around. Like talking about oscillation, it's like they're moving all over. I mean, I don't know, like it's crazy, right? It's just think of it like in a dryer. So the electromagnetic waves coming from the sun, it's like if I just think about this, if I were to take this atom and I know that if it's not moving right now, if it's not moving, these electric fields, they're going all the way out to the end of, to infinity. And it's only at infinity, because you can see the way I'm drawing these lines, it means that, and you actually have an intuition for this. With the sock, the farther away you get from the sock, the less the field is, the less, static force it can apply on something. I'm representing that by the way that I draw these field lines. When the field lines are close together, the density is higher, and that means that the field is stronger. But as you move away from the charge, you can see the distance between the lines gets more and more. So when I'm close to infinity, it's practically zero. And at infinity, the field lines dissipate. That's kind of the theoretical. So for any kind of field, any of these fields, gravity, electric, magnetic, if you start where the field begins on an object like the Earth or the charge, then you have to go all the way to infinity to actually not feel any aspect of that field. And that's why we say that even now, we can, even though it's hard to, we're not sensitive enough to realize it, we are actually feeling the effect of gravity from other galaxies and from other stars and from the stars in the middle of our Milky Way. We're feeling all of that. But it's just not, it's so small that localized gravitational fields like our sun and the other planets and our moon is much larger. And so we don't really, we can't tell that we're feeling those effects of any other fields with respect to instruments that we have sensitivity to. But at some point, we may be able to develop. That's what's happening when we develop these telescopes that are can see farther and farther away. That's actually how they're doing it. They're detecting the fields of those other things. That's what's happening. But we have to make our instrument strong enough to be able to sense it because it's very small. But we can, and we are. Otherwise, we wouldn't be able to see these things with these very more advanced telescopes and things that they're making. They're detecting those small fields, even if they're light years away. Now, that's a static field. Like if we had a chart, if I could take a charged particle, I could put it right here, like just so you could see it, that field would go all the way out to space to infinity and be zero on that infinity. And if I took another charged particle and put it in close vicinity, if it's a positive charge, it would push it away. Just like, I was showing you close to the Earth, gravity causes something to fall. If I were to take a negative charge and put it close to this, like this guy, it would pull it toward it because it can see the field. So the field is actually there. It's there. Now, that's an electric field. Let's quickly talk about what a magnetic field looks like, because I haven't drawn that. It just so happens that gravity and electric fields are very close in their the way their properties manifest, their fields, because these are two different fields. This is electricity, this is gravity. But it just so happens in nature, they look the same. You know, they have what we call mathematical analogy with the way the fields look. Magnetic fields are very different than both of those. Don't want to get into too much, but you know what magnetic fields kind of look like. You've seen the pictures. How would that look with regard to this charge? Well, first of all, a magnetic field is created basically when a charged particle moves somehow, and it can move three ways. It can translate, it can rotate, and it can vibrate. All of those will create a magnetic field with different shapes. But that's basically, you probably didn't know this. Most people don't. How is magnetic field created? Anywhere you have a charged particle, like any of these that I'm representing here, if that charged particle moves, a magnetic field is just created. That's the way our universe works. Yes, that's it. So if I have a charged particle right here that's not moving, let's assume it's not. If I come up to it and I twirl it so that it starts to spin, a magnetic field just appears. I kid you not. That's how magnetic fields, that's how they are created. And so if I spin this thing, let's say I spin it so that if I'm looking down, it's turning, I guess, in the counterclockwise fashion, the magnetic field would just appear and it would look like this. Magnetic field lines are always connecting. So literally, just by spinning this thing, this magnetic field would just pop into reality. And it would be pointing out of the thing, you know, out of the charged particle uh, above it, and then there's a certain direction that the field lines run, and they would be going into the charged particle like this. So this is a shape that's called a toroid. Now this is just two-dimensional, but this this would happen in three dimensions. It would be like a toroid, like a donut, all around it. And also, the electric field is that's just two-dimensional as well. The electric field would actually look like a porcupine if I were to show it three-dimensional. And actually, another thing, everywhere where the magnetic field line crosses the electric field, it would have to do it it does it at a 90-degree angle. Okay, so you can tell that should look familiar. That looks kind of like the magnetic field of the Earth when you see it dramatized, right? And for similar reasons. So, yeah, that's how a magnetic field is created. So, now, what's the difference between static fields and electromagnetic wave? That's what I'm trying to get to kind of build up to give you an analogy for. This magnetic field and the symbol for a magnetic field, for whatever reason, I don't know why, it's historic. I don't know where it came from, but we use the symbol capital B. So for an electric field, it's capital E, but for a magnetic field, it's capital B. At least that's one symbol that's used. Now, static means something is not moving. Now, yes, this charge is spinning, and as long as it's spinning, the magnetic field would be there. But if it's spinning at a constant rate, the magnetic field doesn't change its shape, right? It doesn't get stronger or weaker. And you could tell the strength of the magnetic field in the same way, a similar way as you could tell the strength of the electric field. Wherever the lines are closer together, the fields are stronger. And you can tell that as I move farther away, the lines get farther and farther apart. And again, they're connected. They're not linear like the electric field. They're connected in these loops. But those loops do go out to infinity. And the farther you go away from the source, the more distance there is between the loops. At least that's the way we draw. Now, this is just a graphical way of representing the field. The field doesn't actually do that. It's just a way of showing what the field does in reality. Okay. So as long as this thing is rotating at a constant frequency, we consider that the electric and magnetic fields are static, meaning they're not changing their magnitudes. And they go all the way out and are only zero at infinity. The way I like to think of this is I like to make an analogy between like a spider web. Now that's a two-dimensional representation, but if I were to cut this in, well, this is two dimensions. Like this is representing a three-dimensional figure, but in two dimensions, it's just flat, right? Now, what is it about a spider web that I think is analogous to this picture or can be? Well, let's think about it. If I were to draw a spider web, it looks something like this, right? The spider has these, I don't know, rays going out. I don't know how they build it, but you know, they kind of do it simultaneously. But you have these rays going out. Those would be analogous to the electric field. And then they connect it with these things that come across kind of like this. Now, what's different between the spider web and the actual magnetic field is when these connectors, you know, connect with the rays, they do it with loops like that. That's not really what, if it were a magnetic field, it would be it would be, well, not circular, but it would have to cross at a 90-degree angle. So the magnetic field in two dimensions would be more like that. But still, you can see the analogy, right? So these cross connecting lines in the spider web are kind of like the magnetic fields, right? And they cut across the electric field lines, and the rays, that's what I'm calling them, in the spider web are kind of like the electric fields. Now, if you can imagine that for a charged particle, and remember, it's toroidal. What is toroid? A toroid, again, I think I said it earlier, it's like a donut. So in reality, the electric field lines from a charge, let's say in the sun, point out radially like a porcupine, and the magnetic field lines for that specific charge kind of go out like a toroid, like a donut, but everywhere they cross the electric field lines, they do it at a 90-degree angle. And that goes, and so it kind of just one charge itself, just one, and there's gazillions of them, right? But just one makes a field, if you could imagine, that would be kind of like a spider web that goes all the way out to infinity. That's the static field. And again, I told you, fields are actually interacting with us. We just can't feel them. But when we make instruments, you know, like the Hubble telescope and these other things, we can sense certain types of fields from these things. And so we know that those fields are actually, they're actually impacting us. In fact, you know, don't tell anyone I'm going to say this, but there actually may be some basis to the zodiac. It actually, if you think about it, it actually kind of makes, now, I don't know the mechanics of it, like how they work out, how they interpret it, but just the fundamental idea that, you know, we are physical beings, we're energy, we have electricity, our neural system is electrical, right? And we are definitely affected by physically. Like I'm not saying metaphysically or spiritual. I mean physically, we are affected by the electric fields from everything out there, everything, even if it's not, we're not sensitive enough to realize it. That's just a physical fact. So it doesn't seem completely unreasonable that when a physical being is created at the time of birth, at that instant, there are certain initial conditions. This is just a physics problem. It's how you do a physics problem. At that instant, there are certain initial conditions that govern that system. And those initial conditions are based on all the external forces and fields that are connecting with it. So it's not completely unreasonable when you actually think about it that if you think about some physical thing being brought into or created at some moment in time, that everything at that snapshot, you know, in its environment, and the universe is the whole environment, not just the things in our immediate universe, like our solar system, but everything is definitely affecting that thing physically at that moment. So the idea that that somehow gives it a certain proclivity, that's where it gets hokey. Like I don't know if there's any science that actually is show. You know, I say hokey. I don't want to judge it in that way, but I don't know how you determine based on whatever those initial conditions are the proclivities of that thing as it moves forward in time, which is what um, astrology purports to do. But the idea that that physical thing is being affected somehow, that is completely reasonable because that's actually how we build telescopes and determine things. Like that's what it's doing. So I'll just put that out there that, I don't know, like maybe there is something to that stuff. That said, these fields on this particular example I'm trying, it goes all the way out to infinity at any instant in time. That field looks like that, and it's all over space. Now, think of it as a spider web. That's actually some mathematical spider web or some kind of physical spider web that you can't see. That is the electric and magnetic field that originates at that charge and goes all the way out to infinity. Field, the electric field like a porcupine, the magnetic field like a toroid, and they are connected in that every point in space they're making 90-degree angles with one another. That would definitely be like a three-dimensional spider web because that's what a spider web looks like. Now, here's what an electromagnetic wave is. This is how you can interpret it or ingest it in your intuition. You know for a fact that if you go to this spider web and you see like these wood spiders that make these big beautiful webs between trees and plants, you've seen that in the woods. I know you have. Most people have. If the wind comes along and blows, or if a bee or something is flying along and hits the web, what does it do? It creates a wave that propagates out on the web, just like if you were to drop water in a bucket. And it physically has a physical wave that travels, you can see the thing shakes, right? It's a wave, it propagates out. You take that and make an analogy here that with this field that I've built for you, this combination of electric and magnetic static field, if I come along and I shake that thing, it's going to propagate a wave on that static field all the way out to infinity. And if I keep shaking it, the wave just keeps manifesting. That is what an electromagnetic wave is. That is what's happening in the sun and any other star, any other charged particle anywhere. When it oscillates, assuming that it's rotating, it has both magnetic and electric field, it's sending out a wave that goes on forever to infinity. The neural pulses in your brain, the synapses, when they shift, they send out an electromagnetic wave, and the thing propagates out to the end of space. When you do like an EKG, that's what it's measuring. So that's what an electromagnetic wave is. That's physically what it is. It is the propagation of the static fields associated with charged particles for different systems as they oscillate and sending out a wave pattern. I say that the medium for the wave is the static field. That's just my language. If I were to write a book, that's how I would explain it. But still, conventionally, what they say is that the electromagnetic wave doesn't travel on anything, and I have a problem with that for so many reasons. One, because it's not teachable. It took me years to try to figure out what they were talking about. Like, how could it be? And this is the explanation that I've come up with to be able to explain it to you. And then it occurred to me, well, maybe it is. Maybe that it actually might be the way it works. Like maybe because it definitely has to be a static field before there's a wave. So I think it's a really good way to explain it. So maybe that's what I say, that the static field, for an electromagnetic wave is, but there's other things that we're finding out in space because space isn't empty. There's something called a quantum field that actually is there. You've heard of string theory. I think I might have mentioned in the class before. So, but I won't talk about that yet. We'll just leave it at this. So this is what an electromagnetic wave is. This is what it is. And we can characterize different types of electromagnetic waves because they have different frequency and wavelength. And where does the different frequency and wavelength, how does it originate? Well, in my analogy, when I'm shaking it with a frequency. And that's what establishes the wavelength. Because as that thing propagates, like just go back to the spider web. If you hit it quickly, do it quickly, and you don't like well, actually, the string is a good example. The thing in the gym. If I have really long disturbances, it takes longer for me to make those disturbances. but the amplitude is larger. So a larger amplitude gets for a slower frequency. But if I do it really fast, the amplitude is smaller, but the frequency is higher. And that's the connection. They're inversely kind of related in that way. So if I'm shaking this thing, if I have very large, displacements for and the frequency at which I can do that is going to be slower. So the wave that propagates out will be large waves that move that propagate relatively slowly. That's what radio waves do. Radio waves are at the lowest frequency and the largest wavelength. But something like a gamma ray, is coming from something that's going so fast it's even hard to describe it. And the wave is so small, it doesn't look like, if you would see it, it doesn't even would probably look like a line. Gamma rays are so high that their frequency and wavelength, they actually go through the earth. But that's a different conversation. So yeah, those are waves. That's my overview. And so the visible waves, visible light, that's what we've been talking about here, but all waves behave that, and there are waves that are beyond the visible. But in this chapter, electromagnetic waves are specifically, well, electromagnetic waves, that's a classification. And there are 7 kinds. They're visible, which represented by visible waves, which are represented by the waves of the rainbow. And then there are the other ones. There's, let's list them right here. The different electromagnetic waves. And again, they're all created the same way that I just said here, but they just have different frequency and wavelength based on how I just described it. They originate from a disturbance that was different in amplitude from displacement from equilibrium, and in terms of the number of cycles per second. That's the only difference between any of these waves. So that's what I mean. It's all the same stuff. What stuff? Just oscillating, in my terminology, oscillating static field, magnetic and electric and magnetic fields. So the type of electromagnetic waves that we know of, and this is not in the particular order but you can look at the book. They usually order them in terms of frequency and wavelength. Okay. So as I was saying, so gamma rays, gamma, ultraviolet, infrared, microwave, visible light, radio. I always miss them. What is it? What am I missing? Gamma, ultraviolet, infrared, microwave, X-rays. X-rays are. It's not. This is not the particular order. I should probably look up the order. So X-rays. Yeah, I think it's more like this visible. Microwaves. So I think that's better. So this is in the order of higher frequency and lower wavelength to lower frequency and higher wavelength. And you could probably find in your book where they give you the actual values. That probably won't mean a whole lot for you, but this is more of a kind of a hierarchy. Visible light is kind of right in the middle, I guess you could say. That we're sensitive to. I think Jose, you got your yeah. So yeah. Well, I think it's time for a break right now. What time is it? Oh yeah, we went way past the break. Usually go at 9:30. But so before we take a little short break and come back and talk a little bit, any I can yeah, I'll just yeah. Um we'll do chapter 7 on Thursday, most of it, but um yeah, we can talk. So yeah, so any questions, comments, any gripes? Um uh hey Jose, I think your speaker, your microphone is on. Yeah.
Oh yeah, I see.
Cool. Lizette, how are you? Are you there? Are you there?
Yes,
How are you today?
I'm good. How are you?
I'm good. So talk to me. What do you think about all this? You believe me? You think I'm just making it up?
No, I believe you. I find it kind of interesting, honestly.
Yeah, it's pretty weird. It's very interesting. Obviously, you're preaching to the choir on that one. Yeah, it's like crazy. Like that. This actually, you know, every time I kind of really think about it, and the more that we learn, I'm like, really? This is really is this really like the how things work? Like, and yeah. I mean, I think the book is. Oh, I have this book for my. Oh, this is physical science, but for the physics one class, it's a book called How Things Work. But yeah, this is pretty fascinating, man. It's really, and it gets even crazier, like the implications. Probably we'll get into some of it maybe. Like I think the next chapter on Thursday is relativity. Still kind of looking at it from a conventional relativity. Relativity now is almost 130 years old. Einstein came up with it. And back in the early part of the century, 19, 08-ish, between 1900 and 1895 and 1915 is when he did all that stuff. And for the rest of his life, he was just trying to, figure out some of the problems and issues that came up with it. But the point is that, that was 100 years ago. We've advanced so much since then in terms of what we think is reality. Let me give you, since we're talking about it, I'll talk about this when we come back. I want to say something about the implications of this whole frequency thing. But the thing that I really want you to walk away from, the thing that the book doesn't talk about, book is just straightforward, very conventional, which is good. It's showing you where we came from. But, science and knowledge it's alive, right? Meaning it's always changing, and it's alive because we are alive and we're the ones that move it forward. So any new creative ideas, that's part of, I think I told you early on, a lot of people don't realize that in the way that we think conventional artists are creative, like actors and musicians and things, and there's this creative aspect to evolving music, and moving. That idea is pervasive in anything that's associated with humanity. But there are, because of convention and socio-political maneuverings, certain things are perceived in certain ways. So we don't necessarily perceive science as a platform for creativity, just in the way that we have socialized it and how politics has affected it. And there's reasons for that I want to get into. I don't want to get into socio-political just yet, but there are reasons for that. But just because you believe something doesn't mean it's true. Just because you hope something is true doesn't mean it's true. So when you go back and look and study science, particularly the greats like Newton and Einstein and Galileo and those are the ones that you know about. But there are plenty others who are very, like Maxwell. The people, some of the names I'm mentioning here. These people were completely off the charts creative. Like they didn't view science in the way that we conventionally have do it now. They were very independent. They were very creative. That's how we've made progress. But the point I'm making is that that's still how we make progress. That never changes. So the way that I'm presenting this to you is from a kind of in a way that kind of promotes and hopes sheds light on that creativity. So this analogy that I've made for you to try to explain to you how what electromagnetic waves are, you're not going to see it. I doubt that you'll see it anywhere else. This is me explaining it in my way, the way that I've understood it over the past 40 years. Right? So what I want you to take away from this, specifically on the science, is that what I've explained to you, that's very close, if not exactly how we think it is. And that's really, there's other implications about this that I'll talk about when we come back from the break that are really crazy. But if you can walk away from this, like the book is going to give you kind of a left brain, like very methodical, like, how we, measure it, how we define it, how we can work problems with it. But that doesn't mean that you really understand what it is. What I'm trying to give you is some intuitive basis for understanding what it actually is in a guttural kind of knowing sense, not just that you can know what it is and be able to manipulate it mathematically, but actually, there's a difference between intellectualizing something and experiencing something. Those are two different types of knowing, right? Even though we can't. So what I'm trying to give you is something that's more in line to experiential knowledge based on the thought experiments and the analogies that I'm giving you. So the combination of those two things, I think, those two types of viewing the universe can help, maybe facilitate your understanding in a more comprehensive fashion. So that's pretty much the chapter. I mean, I'll let you read the other stuff they say in there. And they talk a little bit about energy. Not much, but as Thomas mentioned earlier, there's certainly energy. I'll say something about that too after we get back. But before we go to break, any comments or questions, anything you want to say or whatever? But thank you, Lizette, for um, um, speaking up. All right, let's break. Let's go. So 10:18. So
Thank you,
let's
sir.
yeah. Let's take. I need a little bit longer. Let's take about 20 minutes. I need to get a bite. Didn't get any breakfast this morning. So let's take about 20 minutes. We'll come back. All right. So well, what time? Yeah, 20 minutes, something like that. All right. So let's break. All right, we're back. Yeah, so chapter is pretty much done. There is something I was going to say about energy. Actually, energy in a electromagnetic wave is pretty complex, and that's why they don't talk much about it because it's not much you can say about it unless you start to quantify it, and that's beyond the scope of this course. But it's housed in something called a pointing vector, which is just a mathematical thing that describes it. But let me see if I can give you a different way to describe energy and how it's transferred from an electromagnetic wave to an object upon which it is incident. You feel the physical sensation when you go out to the beach and you feel the ultraviolet waves rays from the sun on your skin. And you know that certainly there are certain effects that it can have, right? It gives you a suntan, it can burn your skin if it gets overwhelmed, the cells can't take in too much energy. But it might be useful to talk about in general, not just with electromagnetic waves, but again, symmetry. That's one of the themes of the course. Just in general, how physical things basically on a fundamental level interact with one another. What is the process? And it's really all about energy. It's all about vibration and the energy associated with vibration. Check it out. I might have done this in class before, but it's such a good analogy. I just keep using it over and over. When you were a kid, you used to swing on swings. Those are like the mechanical swings at the playground. Or maybe you were lucky enough to have one of those tree swings with a tire, an old oak tree somewhere at your grandparents' place. And it worked like a simple pendulum. Now, I've already described that when something is swinging, that's essentially oscillatory motion and it has certain characteristics like frequency and wavelength. Let's focus on frequency. Remember, period is time per cycle. Frequency is the number of cycles per second, the number of times it rotates or oscillates per second. Now, you're swinging as a kid, and so that's a kind of oscillation vibration, right? And you have a frequency. Well, you beg your friend or your parents to come over because you want to go higher, and they have to push you. But how do they push you? Well, in order for you to absorb their energy, they have to push you with the same frequency that you're swinging. When you go down, they push down. So the driving force, the thing that's pushing, is matching the internal frequency of the thing that is vibrating. And when that happens, those two objects, the driving force and the system, can see one another and it absorbs the energy. That's how things on a most fundamental level interact. They have to be vibrating with a similar frequency in order to even know that the other is around. Otherwise, it's like the other thing, if the frequencies are so far off, it's like they don't even exist in the same world. They exist, but they can't see one another. Now, the analogy that I'm making here kind of breaks down. Here, what happens is if I go a frequency that's exactly opposite, it actually takes the energy out. So when I push down, it goes up. What happens is, it stunts. So that's not exactly kind of what happens that's it breaks down from the analogy that I'm trying to explain in life, in physical universe when things are free. I mean, that actually does happen. It really does. But that's when the frequencies are still kind of close to one another, but just they're the same frequency, but just kind of out of phase. When that happens, they can interact in a way that's unproductive, basically. I'll just leave it at that. What I'm talking about is something completely different, where the frequencies, like it's so far off that they, I guess the analogy in this case would be like, yeah. So whatever this frequency is, it looks like it's about a half a second or two, 2 or 3 rotations per second. But let's say that I had something like I don't even know. It would have to be something that's just moving really fast. Like this is the vibration, and it's even so fast that you probably couldn't even see my hand moving. It wouldn't affect this at all, right? Because I've got to push down when it's going down, but like in one cycle, this thing is maybe oscillating 80 times, or if it's higher. So it's almost like it's not oscillating at all. So if I touched it, it would be just like my hand. It really wouldn't, it couldn't even match it, right? Because it doesn't even, the energy would not be able to absorb. So it would be like it wasn't oscillating at all, basically. So that's actually more like what I'm talking about. And there are examples of that. The examples are if you take a picture with visible light versus taking a picture with an X-ray. And we know what that looks like. The visible light, what you see is the surface of my skin is interacting with, you can't see anything internally. But if you take an X-ray, all you can see is my skeleton. You can't see the organs or anything like that. If you take it with, what's the other thing? The scan, those are with the CT scan. I think those are. Is that infrared? It's not infrared. I think it's. Actually, I forgot what a CT scan, what the CT scan. I forgot what those were. What the it might be. Is it radio waves? It might be. I can't remember. Anyway, the different waves, you see different things. And it's really interesting if you take a picture of the sky. I think we probably can Google it. Point a camera toward the Milky Way, toward the center of the Milky Way galaxy, and take visible light, then ultraviolet, and then X-ray. And you look at the pictures; they look completely different because obviously the X-ray can detect things that visible light doesn't. But the thing that I want to impress upon you is that those things that you can see with the X-ray, those are physical things. They have a physicality. Otherwise, we wouldn't be able to detect them. But relative to those things that you see with visible light, those two objects are so far away in frequency that they can't see one another. Like if they could see, whatever they are, whatever they would be, they can't interact at all. So it's that not even physically. So it's as if those things don't exist in the frequencies that correspond to the X-ray as compared to the visible light or whatever. That's how different it is. Now, we kind of only think about that in terms of light, the different types of light, because that's the only thing that we experience with it, at least consciously, in our reality. What quantum mechanics is saying, and this is kind of a big deal, is that pattern that we're talking about with light is a symmetry for the way everything behaves in the universe, even though we don't really perceive that. What I'm trying to say to you is that when we talk about the visible spectrum of light and compare that to the spectrum of light that is includes the other seven waves. What I'm saying is that with light, we're proposing that there are other spectrums even beyond the spectrum that corresponds to the spectrum that goes from gamma to radio waves. There are waves down here below that we can't detect, and there are waves up there that we can't detect, and they go on infinitely. That's what theory predicts. That's one thing I'm saying. But I'm also saying something else. Everything in the universe is energy. And on a basic scale, the analogy that I just made here with you with an electromagnetic wave. So that's the source of the frequency associated with the electromagnetic wave in light. But what is the source of the frequency of everything else? Actually, even including light. Because the atom itself is actually, and the electrons and the protons, that's not the smallest thing that exists in the universe. There are things that the protons are made of, elementary particles, bosons, hadrons, you've probably heard the names, and we can break them down and figure them out. But there are even things that the elementary particles are made of. So when you go down to the smallest aspect of what's in the universe, that's what we talked about a few weeks ago, maybe. I don't know, I can't remember if it was this class. But they're called strings. That's one way to think about them, as in string theory. What we propose is that on the smallest measurable increments of measure in the universe, there are corpuscles of energy called strings that are kind of similar to the strings of a strings instrument. And they're just vibrating corpuscles of energy with certain frequency and wavelength, just like what we described here. And they come together in certain ways that we don't really know how. We're trying to figure it out. But they then begin to form what we see as the subatomic particles that's inside of a proton and a neutron. And then those subatomic particles combine together to give larger subatomic particles, which combine together to give atoms, and atoms combine to give molecules, and so on and so forth. But the smallest building blocks of the universe is just energy. Everything really is just energy, and is defined, again, the analogy is good, that I made with how I described the wave here, because that's still a way that we can describe the energy associated with the vibrating corpuscles of energy, the string. And it's called different things: string theory, quantum field. You might have heard that term before in movies and things. Quantum field theory. It is the physics of trying to figure out how these corpuscles of energy, which basically fill the universe, they're everywhere. They're around us. They're in us right now. They're in between the atoms of our bodies. It's everywhere. It's kind of like if you're in the ocean, you can't see water molecules, but you're in the water. That's what it's like. That we're immersed in the quantum field theory, and it goes from the point right in front of you out to the farthest edges of the universe. It's everything, and everything in the universe, stars, galaxies, everything comes from these corpuscles of vibrating energy. So that's what I was alluding to earlier. We don't say that space is empty anymore because it's filled with the quantum field, which is just these corpuscles of vibrating energy. Now, the reason I mention that is because I want to extend what I'm just saying about light. Light is a really nice thing to study, and for me to explain this, because we know what light is. We experience it, like it's everything we're using, from our cell phones to the lights in our house. It's this stuff that we just talked about. It's electromagnetic waves, right? And and I've now described to you the difference between a static field and an electromagnetic wave. A static field is this, the field associated with the source of the electric and magnetic field. And if you vibrate that, then it can cause that static field to wave, and that's what an electromagnetic wave is, as we talked about. Now, similarly, so what I want to focus on just right here, this point I want to make, is that I talked to you about how we can then describe the spectrum of electromagnetic waves. There's a visible spectrum that our senses can see. It's very short relative to the overall spectrum. It's right in the middle. But we can develop instrumentation to detect these other waves. And theory speculates that perhaps there's even waves that are much higher in frequency and smaller in wavelength, and some that are even lower in frequency and higher in wavelength beyond the spectrum that we know. That's just light. Now, with the strings in quantum field theory, take the analogy that I just made with light coming from vibrating electrons and protons. And the big leap that I want to make here is that matter, M-A-T-T-E-R, is essentially the manifestation and the combination of different frequencies in the quantum field. As Einstein said, E equals mc squared. Energy equals mass, my fingernail, my hand, your hair, this pen, times speed of light squared, which means that mass, anything that you can see around you, is really just energy. How? Because it's made of those strings of energy vibrating in the quantum field. Those things come together, slow down, and start to make what looks like matter, the subatomic particles, which make the atoms, the protons and neutrons, which makes the atoms, so on and so forth. So everything around us is built from quantum field, which is just energy vibrating very slowly with different frequency and wavelength. So the pattern that we use to describe light, it is literally the pattern of the fabric of the universe. Everything is just light. Everything. I'm light. It's just that I'm light that has slowed down very slowly and is vibrating with a different path. So it has a different characteristic. In the same way that visible light seems to be very different because it has different characteristics from an X-ray, extend that to everything. Matter is just light with a very different characteristic, seemingly, because its frequency and wavelengths are so different and so much more complex than even just light, which is complex enough in itself. But it's still just, that's what theory is proposing. Now, if that's true, and I believe that it is, or at least something like it, we can extend the analogy even more. In the same way that I've made categories of frequency of light, which their categories are very different, even though it's just the same stuff, right? It's, they're just a small difference in frequency and wavelength manifests so differently in the way that we perceive it, i.e. the picture of taking me, an x-ray of me versus a visible picture of me. They completely look like they're completely different worlds. What if we saw an x-ray only? Our world would look just like those pictures. And the picture would be very different. The visible picture, when we see it, he's using an instrument to take a picture with visible light, it would look crazy to us, just like, and we couldn't even imagine living in a world like that, just like it's hard to imagine living in a world where we only see x-rays. But again, it's just a slight difference in frequency and wavelength, even though it's the same stuff. So if there's that much difference in the perception of visible light versus X-ray, and it's so much closely related in terms of its physicality and the way that we describe it mathematically, just imagine how different the universe would be if we're talking about, or the perception, if we're talking about, the differences in frequencies of vibration of the quantum strings coming together and forming different things. Well, that is what we're perceiving. That is why I might look very different in constitution than something like a star, or even objects here, like a metal versus what we consider to be biological material. It's all the same stuff. It's just, but it's just combined frequencies of oscillating strings of energy on the quantum level that have combined in such a way that they're manifesting with an overall frequency of vibration that's very different and looks like it's something completely different from my fingernail. In the same way that visible light is different from ultraviolet light. Now, if you can grasp that, here's the level that I really want to go to. Visible light is a small part of the overall electromagnetic spectrum, the part that we can see. If we can make an analogy between matter in terms of vibration coming from the quantum, originating from the quantum field, this always flips me out just really thinking about it. What we perceive as the universe that we can see, what we call reality, all of that theory is suggesting is just a range of frequencies that is close to the frequencies of anything in our physicality, which is why we can see it. But it doesn't mean that all those things that we experience as part of our reality is the only frequencies of reality that are in existence. In the same way that there are different frequencies of light that we couldn't see that we thought was magic or something before we had the instrumentation to see it. And now we just take it for granted and we realize it's just something outside of our sensibility, our visible light. Well, the whole universe, theory is suggesting, is made that way. So there can be conscious things, entities, whatever, that are real and just are vibrating at such a higher frequency or much more lower frequency of matter, not light, that they exist, but they're just in different, well, what we call is dimensions or densities of frequency. That's the term that it used to be dimension, but people confuse that with spatial dimension. When people talk about the universe being different dimensions, they don't really mean spatial. They mean vibration. It's what I'm saying here. It's like everything that we see is vibrating with a certain frequencies within the range that is what we call matter in our reality. But we're now beginning to realize there might be frequencies of matter vibration that is so high or low that it's beyond what we can physically perceive or even what the instruments we have created at this point to perceive. But they are there. And if they are there, what it means, well, let me go back before I make this point to an analogy of a gamma ray. We know that there are gamma rays. They come from the sun. When there's a big solar wind, they come in. Now, you might have heard that some of these waves, because there's frequencies, there's ranges, even within each of these frequencies, there's ranges. So in each, like just like we can split the visible light range apart, and it goes from purple to green, from red to purple. All of these have ranges where there's different ultraviolet ranges of ultraviolet rays within that spectrum. There are some gamma rays that are at the top of the spectrum that are so powerful and so the frequencies are so high that they go through the earth. But what a lot of people don't realize when they hear that statement, I'm sure you've probably heard that before, is that if you were on the gamma ray, right? Einstein said that he visualized relativity by surfing on a light beam in space. Now, when we say that, we just kind of say, oh, well, I'm surfing a light beam. But I think Einstein's brain was such that when he imagined it, for him, it almost became real. And so that's how he could come up with these. He was basically experiencing it just like it really happened. So in that experience, he could see things that many of us don't see because it's hard for us to train our minds to be able to visualize something with that kind of visuality. But my point is that Um, when we actually, I forgot the point I was about to make. Yeah, what I was trying to do is create a thought experiment where I visualize you from the perspective of the gamma ray that's coming in. If you're coming from the sun and you're a very high power gamma ray, you're going to go through the earth. But when you're going toward the earth, what do you think you see? And remember, the idea is frequency. Remember this analogy, right? When the frequencies match, they can see one another and they can interact. But if the frequencies are so high, so different, they don't even interact. So if you're a gamma ray and you're at such a high frequency that you're going to go through the earth, when you're actually going toward the earth and you're the gamma ray, what do you think you see in the space of the earth? Anybody? Just guess. Let's see. Uh, Jamie, you haven't said anything today. Are you there? Jamie, are you there? What about you? Erica, are you still there? Oh, is Jamie there? Who's talking?
Yeah, I'm sorry. I'm multitasking.
Oh, yeah. Can you do you can you answer the question, or you want to give it a shot, give it a stab?
I honestly don't know. I have a lot of revising to do,
A lot of what?
like going over stuff to make sure I really understand it.
Okay, all right, fair enough. Erica, you wanna give it a guess or a shot, or maybe you know?
Maybe waves or nothing.
Awesome, bingo. Second one, nothing. You don't see anything. Good, very good. If you're at such a high frequency that you're the gamma ray, there's nothing on the earth that has the frequency that corresponds to you. So you don't even see it. Nothing's there. That's why it goes through. We don't see it. The only reason we begin to know is because theory began to speculate, and then we made instruments where the instruments have, mechanisms in them that vibrate at that, can vibrate at the frequency whenever the gamma ray hits it. That's the only reason we know that it's there. We can't see it. It's not there. It's in a different universe. It's only in the universe that corresponds to those frequencies. Now that's just light. That's light. If there are conscious aspects and conscious beings and aspects, things in the universe, even physical things that are in the universe, such that their essence, their vibration is so high that it's different than ours, it could be right around us and we wouldn't even know it. That's what we think the universe is. And when now in movies, when you see people talk about traveling to different dimensions, that is what they're talking about. That's related to time, because it's related to, we'll get into it later, but it's related to time and different things like that. But when you're talking about the universe is different dimensions, they're talking about frequency dimensions. That's what it is. And again, it's just crazy. It's insane when you start to think about the implications of this. Because when you go back and if you understand that that's science, that's true, then you start reconsidering all these things that formerly were thought to be nonsensical, like ghosts or entities, and even, or non-science, even if nonsensical, like angels and things. If you have conscious aspects of the universe, beings or whatever, that are at higher vibrational frequencies in terms of their constitution. And what if they can control it? Like, because we even say, like, some of the more metaphysical and philosophical aspects on Earth say that there is something called a vibration in your body and you can control it. Science is only really catching up to that now to be able to measure these things. But Western philosophers and, Buddhist monks have been saying this for eons. Not only do you have it, but if you meditate, you can control it. And if you can control it, you can raise and lower your vibration. And that allows you, like all that stuff now seems to make somewhat sense. That science is somewhat corroborating that. But let's just say that that is true, that you can control. It's definitely true that things have different internal vibration. That's science. The fact that they can be conscious, that there are other beings, we don't know. But I'm just saying that now it's possible, I think. But if you could control it, that means that just like in science, where when you get to one cusp of, the border of a certain range of frequencies, it doesn't just stop and then you go to the next one. There's a cusp in between every range, so that there's some X-rays that then bleed over into ultraviolet rays and back forth until you get very well into that, that range of frequency. That's straight up science, and everything that abides by frequency, and basically that's everything abides. It can be described in that way. There's always cusps along the borders of different frequency range. In fact, there really is no frequency range. The only reason that we call it a frequency range is because we like to say within this range there's certain characteristics that we perceive. But it's just an infinite spectrum. We're just breaking it up based on how we like to use it or see it. And every spectrum of frequency you could say that about. So with matter and reality, that would also be the case. So let's say, everything that we're in our world, we usually call three-dimensional space-time. Like that's what Isaac Newton, Einstein called it, space-time. And we call it three-dimensional. And again, there's a confusion where I'm gonna start using the word density, because I mean third density, meaning everything that's us and in our reality. Well, there's a fourth density, a fourth dimension, which means that those are things that are hot, that are vibrating in a range, whatever the range is associated with fourth density. And I don't know numbers or anything, but just let's say that exists. Well, what happens on the cusp? Maybe, and I'm just proposing here, maybe some of these phenomena that we call extraordinary, even some things like sensibilities, like ESP, and maybe these are happening with abilities that somehow are on the cusp of these higher vibrations. That something in us, maybe people are born, I don't know, like are born with some sort of physiology that allows their frequency associated with their physiology to be a little bit higher than us in their brain activity or whatever. And so it causes them to be able to access aspects of our ability that most of us can't, because there's nothing in our physiology that's vibrating at that frequency. So things like ESP and communicating, like, I don't know, maybe that's how it's happening. This is but certainly if there is something like, I don't know, ghosts or something, inanimate objects, they're only inanimate because they're in a frequency, maybe, that is higher than something that seems real for us or as part of our reality, because everything in our normal reality is vibrating with the normal frequencies of our third density, of the density or the plane of existence within which we live. And so if something can control it, maybe it can kind of slow its frequency down such that it begins to manifest into our reality, and then it can raise it and go back. I don't know. I'm just simply saying that what is true, what is science, is that we have different densities in our universe. And in terms of matter, what that means is these things are vibrating at overall different frequencies as they manifested themselves from the quantum field. And if that's true, that means that there are all worlds out there in these different densities, just like in the different frequencies of light, that all basically everything that's happening with us, the same types of things could be happening in those frequencies of reality. Yeah. What do you think about that?
Well, I think it's like God and spiritual, man.
Yeah, it's mind-boggling. Mind-boggling. Well, that's an overview of waves. And I hope that you found it interesting. Much of that, the latter stuff that I mentioned, we haven't fully, it's theory. We haven't proven it. There's nothing that I know of that is, and actually we may have. I think a lot of this stuff, some of these government funded programs, I can't imagine. I'm just one dude, and it has a little bit of knowledge, with my PhD. I've been thinking about these things. I'm very interested in it. And I just can't imagine that somebody else hasn't thought about this. And if those persons or group of people are in a position where they can start to test, I'm sure people, if I had the money and the time, I certainly would. So I'm certainly sure that I believe that people have. And if you begin to verify some of this, I'm not sure that people would let it out. I'm not sure that, if it's done on the government level and government projects. I've actually worked at a few labs. I worked at Los Alamos Labs for a couple of years. And I kind of have an idea about how these things work. I'm not sure that these people, that they would tell people, that we would let it out, because, knowledge is power. And it's just so, it's just so crazy compared to what our reality is. I don't know. I don't know. Like, I have a feeling that we have advanced much more than what is actually out, in our kind of everyday lives. Because, and you can see it in the movies, right? Like, you look at, I think I talked about, you look at stuff like Star Trek I used to look at when I was 4 or 5 years old. And the guy would break out his transponder. You look back at that now and you realize that the transponder is literally just a combination of a flip phone and a smartphone. And that was the late 60s, which means that they already knew what those things were, but these things didn't come out. The flip phone and the cell phone didn't come out until 25, 30 years later. So if that's in any way an analogy, I mean, you look at any of these movies now, with what they're doing, and they're talking about exactly what I'm talking about. Like, there's basis, like, you know. So if that's any indication, we're at least 30 years, more advanced than probably what the average thing that's coming out of the movies, but maybe more now, maybe 40 or 50 or even more. I don't know. So that's why I believe that, a combination of those things, that people probably have made some inroads into investigating some of this, but it's not being put out, because the implications are it's just mind boggling. Like, it means that, yeah, I don't even want to go there. But I do believe that what I have outlined for you, or at least something like it, is actually the reality of what we're living in. And so, uh, hopefully we kind of bring it back to practicality. What is known, what is being taught, is how they lay it out in this, this chapter with electromagnetic waves. But I think it's a really good opportunity for me to let you know that the basis of electromagnetic waves, which is ultimately vibration, basically what it means, what is that the most fundamental property in the universe is frequency, is vibration, from a physical point of view. Because not only does it form the basis of how electromagnetic waves are formed, electromagnetic waves, what I've done for you in this lecture is use electromagnetic waves as a model for how everything in the universe, even things like this piece of metal podium, which doesn't look like it's vibrating, how actually it does come from vibration, and it really is just energy that has come from corpuscles of energy in the quantum field that just have combined in such a way that they form what looks like the properties of this seemingly solid material. So Yeah. I hope that's helpful for you. Gives you something a little bit to think about. And you can continue reading the chapter, and the homeworks are open. I'll go over Einstein. I think the next chapter deals with Einstein's relativity,
I have
and
a
we'll talk a little.
question.
Yes, go for it, Jamie.
So with like the understanding of waves and stuff, what would you classify your thoughts as?
Oh, those are well, people call them brain. That's a good question. Um, People usually focus on that in the medical world, and they just call them brain waves. So when you do an EKG and that little thing, that's a two-dimensional representation of brain waves. The little, I'm sorry, that's a heart. Heart, that's a heart. But you can do something similar with the brain. Usually, what people do is they show you those pictures, those brain pictures with the colors, or maybe an MRI when you see the colors. Uh, was the MRI is really it's showing pictures literally of the brain, but there is I forget what it's called. It's not an EKG. It's something, but it's in some of these they when these put these electrodes on your head, right, and you do like a test. I think they usually show a two-dimensional picture of different like they'll ask you a question or they'll have you go to sleep if you go in some of these science shows, and they'll show different brain activities occurs when you're doing something like having REM sleep or whatever. Different parts of the brain are being active. What it's those are brain waves. They're taking the electrical impulses. Those electrodes are getting fields, electric fields that are coming from the electrical impulses of the neural activity in your brain, and they are making then that sensor is turning that signal it's getting from the brainwave into a picture associated with the color of certain colors and pictures associated with the brain. So basically, I think it might be radio waves. I'm not sure, but basically, it's the same. Like when you have your remote and you hit your car, right? It sends a wave, and there's a sensor in the car that takes it. Those electrodes that they put on your head and then ask you questions or have you go to sleep and perform different activities, you're having neural activity in your brain, and when those like an electron moves, it creates a wave just like I showed you here, and that wave sends out a wave like that goes out to space, but that sensor picks it up because it's tuned to a specific frequency, then converts it to a picture that you see on the screen. So it's a brain wave, but what is a brain wave? It's just this. It's just the neural network in your nervous system in your brain, the synapses, popping off and doing their thing. And when they move, or when they, certain thoughts or the way, basically that's what a thought is physiologically. It's just uh, neurons and the neural system becoming active. When charged particles move in that process, it sends off waves. And those waves have specific frequency and wavelength associated with that activity. And that's what the sensors are detecting, and then convert that to a picture that we then read. So the short answer to your question is that it's a brain wave. The qualification is, how is a brain wave different from these waves? It's not different. It's literally the same thing in terms of how it's being created, but there are characteristics and frequencies and wavelengths specific to your physiology that we refer to as brainwaves. Yes.
By that logic, then you can kind of prove manifesting and like that it's like real through physical science.
Say that again.
Like, people be like, oh, like, the things that you say, your thought process, the questions that you ask in life kind of helps in a sense manifest your reality. Because so if your brain, then the thoughts that you have is giving like a radio transmitting frequency. If you constantly think bad thoughts, or for example, like if people are always calling themselves like broke, it's like kind of getting yourself stuck in the energy of like not finding more kind of like financial troubles, because it's like, yeah, that's kind of what you're telling yourself, kind of like that's what you're admitting, like this is like what you're telling not even the universe, but that's kind of what you're trying to match to. versus like, being careful with your words, because words kind of in a sense are also like spells, because words themselves have a different frequency and wave. So then it's just like, instead of saying that, be like, oh, I'm in between blessings, because it's like, something's coming, you just don't know what it is. So it's like, it's in that energy of the waiting instead of being in the energy of definite.
Yes, yes, Jamie, that's wonderful. That's very perceptive. Now, what I want to say, I'm going to have to say this in such a way that kind of scans between two worlds. Everything I would say to you is yes. However, science, as to what we've been told is science, has only proved certain things and hasn't proved others. And that's what I'm trying to show to you, that based on what I just told you, yeah, that is the next leap. That if everything is just energy and it's really just vibrating corpuscles of energy that sends off fields, and we know that fields interact. We see that with two magnets that can interact without touching, or with fields associated with static electricity. If that's what it is, then if that's how fields interact, and our brains are giving off fields that are actually things, just like some people, some gurus have said in the past, thoughts are things, then yeah, it's not unrealistic that you can actually communicate and manifest with your reality just from thought. It's just the next leap. And yeah, Western philosophical and people have been saying that literally for thousands of years. But science has denied that and still does. Why? Because according to science, we haven't actually proven that that's the case. But I would offer to you this. Even things that for some reason, and we won't have to get into that because that's a whole nother ball of wax. But for some reason, consistently throughout history, there's been this resistance to evolve. That's why Galileo was thrown in jail and died in jail, house arrest, because he said, the earth is not the center of the universe. That still very much exists. So yes, your logic is completely, and I'm with you because I actually believe it does. But as a scientist, I cannot say that it does, because there is nothing that I know of that we have done, or at least that has been published, that has shown and proven how a thought can manifest a reality. But theoretically, not just from philosophical speculation, but based on what theoretical science is actually saying, there's no reason why it wouldn't. Absolutely. That is the next logical, uh, in my mind, logical supposition, that what's keeping you from being true? I don't think anything. But I don't believe it has actually been embraced by science or proven in any way that has been publishable or repeatable. Does that make sense?
Yes, but at the same time, I feel like there's so many books, not necessarily science books, but like books where you can like see this phenomenon existing. Like, for example, over like a couple of my summer reads, like I read like The Big Leap by Gay Hendricks. And basically his whole thing is that, like, the four reasons why people's lives don't improve, or like, they end up, you reach a lot of success, and then like if something happens and then everything just messes up, is because they are afraid to take the big leap into their zone of genius. And that we all have four different zones, like there's a zone of incompetence, zone of competence, zone of excellence, and then zone of genius. But so many people, just due to childhood conditioning, they get stuck at the bottom three, and they never really reach that zone of genius until you take heed onto things that satisfy you, and only learn how to say yes to your bodily yeses, and then like say no to things that, like, don't make sense. And from a human design standpoint, that makes a lot of sense, because, like, human design is like the study of energetics, and like how people's bodies can like literally tell you, like, how to get the things in life with the least resistance, well, on the path of least resistance. And then the other book too, which is a popular book of The Secrets, which is basically the whole book of like manifesting, which again is kind of like the whole theme of like, your brain. If you think a certain thing, that's going to happen to you. If you are more powerful than your brain, which we still need to do more research on as well, because there's a lot of misconceptions, I guess I want to say, with the brain. And like in terms of like people say that we only use 10% of it. Which is that true? Do we only use 10% of it? Like, is that an absolute truth? There's no such thing.
That is true.
That's
That's true.
absolute
Yeah.
truth.
Yeah. I mean, that is what science is saying. In fact, not only use it, the other 90%, we don't even know what it does. So the reason that we say we don't use it is because we don't know what it is. We don't even know science can be so arrogant.
Mm-hmm.
We don't know what it does. So we just say, oh, well, maybe we're not using it because we don't want to admit that we don't know what it does. We don't know. We don't know what we're using and what we're not using. But on average, we
Mm-hmm.
can tell that we have an idea of what 10% does. So then we say, well, we're using 10%. That's really what science says. So the answer to your question is yes, but it's even more somewhat hypocritical than that because we don't really know. But what we think we know, we say is 10%.
How will we know what more than 10% looks like?
It's just evolution. We have to evolve scientifically. So we have to figure out ways of testing. We have to develop instruments that do test and make sure that the test is measured. It's just slow progress of evolution. Maybe in 20 years we'll know what 12 or 13 or 14% does. But right now the standard is about 10%. It's just evolution, just like anything else.
As also, is it true that nothing is ever 100%?
Yes, that is true.
So nothing can be an absolute.
That's right. There is no exact science. That's not true. Science is not exact. In fact, science proves to you that there is no exactness. But what happens is there's always a certain amount of error. But what happens is within certain ranges of orders of magnitude, the error doesn't matter. For example, when Newton came out with the equations that well, let's say the kinematic equation, velocity equals distance divided by time. That comes out of Isaac Newton's mechanics. He did that in around 1600-ish, and for a couple hundred years, everybody believed that. Then, in the 1900s, people like Einstein and those people came along. We got technologically advanced, and we started being able to make really precise instruments. And we started to try to apply velocity equals distance divided by time to really small particles like protons and electrons moving very fast, a third of the speed of light. Turns out velocity did not equal distance divided by time. Because on a quantum level, there's other kinds of physics going on that when we use and it's going on now because we're all made of quantum particles, but we're at an order of magnitude where the quantum world is not obvious. So the error in the equation of velocity equals distance divided by time is actually distance divided by time plus what turns out to be quantum terms. But those quantum terms are so small. It's like if the actual answer is 5 meters per second, the error would be 0.0000, I don't know, whatever, something that's so small it doesn't manifest. But when you get an instrument and that you try to use that equation for a quantum particle, which is very light and going very fast, that error becomes huge. And that's how we were able to see that Newton wasn't quite right. And we could never see it until we developed enough where we could have instruments that could test it. So then Einstein, with his relativity, made corrections. And the corrections actually worked, such that it's velocity equals distance divided by time plus some quantum terms that we'll maybe talk about in a couple of chapters, or maybe next chapter, that when you put those terms on for a quantum particle, they get exactly right. And when you use that same equation for macroscopic, for our everyday lives, you can still use the equation, but the term is so small that you might as well not use it at all. So that's an example of how, as we progress, we have to kind of make adjustments to things and how, something can be partially right, but not fully right, or how science it looks like it's exact from a certain point of view. But if you look closely enough, it might not actually be exact, but the exactness or the error is just insignificant for whatever you're using it for. But if you need to use that same equation or same concept for something that's more precise, you might have to come up with some new science to tweak it to make those corrections valid. And on every level of science, that's true. That's why it's not exact. So, like, if we go to the quantum world, we got those new equations now. But there might be a tone, 50 years, 100 years in the future where we can go even smaller, you know? And when we get to that level, the equations that we develop for quantum mechanics, we find that they're not exactly right. So then we have to develop, tweak them even more. And it just goes on for infinity, basically in both directions. That's what the universe is. That's why it's no exactness. It's just exact within the order of magnitude of your reality being what your natural perception senses can perceive. Does that make sense?
Yeah.
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 That's really what the universe is. There is no exactness.
Yeah.
Everything just
Recently I was
repeats
forced to
itself.
watch Interstellar. And it's a very mind-boggling movie.
Oh
I
yeah.
liked it, but it was just a lot. It was a lot.
Yeah, that was really good. Yeah.
Giving like the similar to Insidious, but like the third one, which really threw me off. I was gonna get like that. I was giving more sci-fi than giving horror at that point because it just tied in all the three movies together.
I didn't see I just saw the first one. Haven't seen the last couple. But yeah, it's really interesting how you see science start to manifest somehow and trying to make explanations for these things in movies. Interstellar was really good. I really like that one as well. There's other things that I'll talk about later. When he was in the black hole, he could see all the different possibilities from what he had seen. From the closet thing. That's something to talk about. That was really interesting. Also, the picturing the black hole. I think that was the first time that a black hole was ever uh, uh, presented, in media anywhere. And now, whenever you see a black hole, it always looks like the one that was in that movie. But that was the first time that an event horizon of a black hole was dramatized or illustrated in a three-dimensional film like that. So now it's the standard of what a black hole looks like. So it's so interesting.
So we don't know what it looks like?
No, not really. We can't see it. You can't,
Oh.
because light can't escape. So it's just a theoretical representation. What you're looking at when you see that picture, it's just the surface of the black. It's just the beginning of it. It's called the event horizon. The black hole is actually behind it. But what happens is when light goes through, light has certain kinds of behavior, and some of it is lost. And so what you're seeing is kind of like residual of all the light. Oh, what just happened? Oh man, I forgot to plug in my computer, so it just ran out of use. So I think I got the other two cameras up, so I just keep talking with those. Yeah, the event horizon that you see in the black hole is just the surface of it. In fact, it's not even the black hole. It's just the light that's actually it's the residual of the light that's actually going through the black hole. What's left of it after it goes through. And theory talks about that. But yeah, we don't know what it looks like. You can only speculate theoretically of what it's inside or what happens when you go in.
Has anybody ever tried to go inside?
No, we've never found one. They're way out of way someplace. Well, actually, that's not true. You can make different sizes, and you can actually make black holes, I think, in the lab, and they've done it in some of the labs in
You're
Europe.
so right. What is it called? Oh my God, them. It's like this funny thing that not running on Twitter. They normally have it. I think it happened like 2 years ago.
Yeah, a few years ago. It's happened quite often. There's
They
many
did it.
black holes, but they're so small, and then they disintegrate, very quickly. So they're not really dangerous to us. But the black holes that you're talking about, like they're they're. I don't know where the nearest one is, but they're really. Actually, the nearest one. Every galaxy has a black hole in the center. So the nearest black hole to us is sustainable black hole. Is in the middle of our Milky Way. And as far as I know, I think that's all of that's as far as I know is where black holes exist, are in the middle of galaxies.
Right.
I'm sorry, I cut you off. You going to say something?
No, you're good. I was trying to remember what that company, not company. I think what are they called? I was trying to remember what that facility was called.
Maybe CERN.
There we go. Yes, it's that one. They were saying because they were talking about. I don't know if you ever seen that the Simpsons theory either.
No.
about how like the Simpsons TV show has predicted so many future outcomes and like subliminal message throughout the show. And then one of them were like a really old episode of CERN and how like they every time they do the little particle thing that they keep messing up the timeline, which is why stuff just keeps getting so hectic. They keep blaming the timeline change up on CERN. I'm just like, honestly, at this point, blame it on somebody. I would not blame it on somebody.
You know, again, you see that a lot in movies now. That's a big deal, like flipping timelines and manipulating timelines. Honestly, they say that's, theory says that that's true, and you wouldn't know. You wouldn't know, like, what if it's already happening?
Oh, the Mandela effect thingy.
Yeah, the Mandela effect is one of the popular things in popular culture of how that. Yeah, I didn't know that was a thing. Like, I don't, I don't. Yeah, I didn't. I've heard about that, but that's not something that I personally experienced. Um, yeah, but maybe I guess if I was on the, yeah, I don't know. I had you. Does that resonate with you? That whole thing with that? In fact,
I
why don't you
kind of looked
explain
it
to the class
up.
what the Mandela? Many
Uh,
people may not know. Can you explain to the class what the Mandela effect is?
Yeah, the Mandela effect is like when you remember certain things a certain way, but other people can remember it totally different, and y'all could be born the same year or whatever, but it's just like not different, not the same. Like some people remember like Fruit Loops spelled a certain way, like FRUIT loops, and then other people may remember as like FROOT like loops. And then the Berenstein Bears versus Berenstein Bears, whether who was it? I think it was like Jiffy versus Jiffy, just like certain brands. So like even these like your cartoons as a kid, like Pikachu, like whether Pikachu had a black tail or didn't have a black tail. It's just really scary, but teach their own. I don't know. Oscar Mayer versus Oscar Mayer, Skechers logo. For me, it's Monopoly. I could have sworn Monopoly had a monocle, but now they say that he doesn't have a monocle. So I'm just like, I wouldn't be surprised if my timeline changed at this point. I'm hopefully I did, but we don't know. Monopoly Man doesn't have a monocle.
Really? Because when I was a kid, they had a monocle.
Yeah, but if you look it up right now, like Monopoly Man, he does not have not have a monocle in any of the brand thingies.
So how do we know they didn't change it? They say they never changed.
Yeah, it said they never changed. And I'm just like I could have sworn
Monopoly
Pikachu had a
Man
black
definitely had a
tail, but now
monocle when I
Pikachu
was a
does not
kid.
have a black tail. It's kind of scaring me. And yeah, Monopoly doesn't have a monocle no more.
That's really weird because, yeah, I played Monopoly with my cousins all the time, and that dude definitely had a monocle.
Yeah.
I didn't know that because I don't play much anymore,
Like
and I
whenever you
didn't. I
put
haven't seen
Monopoly
the
on
reason.
Google, the first thing that comes up is Monopoly Mandela effect. Because everyone's
Really?
like, I could have sworn this man had a monocle. Yeah. Probably one of the most common one, just Monopoly Man.
Well, there you go. It is kind of. I don't want to use the word scary, but it's just reality. Like once you kind of become aware and you start thinking about these things, it's kind of becomes normalized within your mind. It's kind of like what you're saying about having your energy and focusing your thoughts and manifesting. But I can tell you this: there's been a certain few things that have happened over the course of my life where you know, again, as a physicist, I cannot say that it has been proven from a scientific point of view, but from my personal experience, there are things that have definitely happened. I'm an objective person. I was there. I was involved. It happened, and there's no scientific explanation for it other than what I've been talking about, which hasn't been proven. And
Mhm.
so, that's how you move forward. You just, what is true for you, you just move forward with it. That's how I've had to operate. You don't have to argue with anybody. You don't have to you just, and that's the power of science is that I do believe thoughts are real. So if you can focus your intention and your thought to create your reality, in fact, and I guess class is about over. I would leave class with just this thought. We're in our society we're in turmoil right now, and it's not just relative. It's actually worse. Like I'm 69, right? And I've talked to a lot of people. I've kind of, talked to older people, like in their 90s, just to kind of get a relative because there are things that happen. When I was a kid, I lived through Watergate. I remember coming home from school and watching it every day when I was 7 or 8 years old. That was really bad. I was born in '64, so the first 7 years of my life, Vietnam was all on the news, like the way things, the news is now with the war and stuff. That was the first 7 years of my life, and it was pretty scary. Watching and understanding that we were at war, and the troops didn't come home until I was 72. I was 7 years old. I remember the day watching it on news, right? So I've always been pretty inquisitive, and I remember these things, right? Because I was interested in them growing up as a kid. So now when I look at how our world has changed in the past 10, 12 years, it's kind of hard to see, well, is it actually worse than it was back then? Or is it, because it was pretty bad back, those things were pretty terrible. The threat of nuclear war, all that stuff was real. Um, is it worse now? Is it really a little bit crazier now, or is it just like seem that way?
Crazy.
Everybody that I've talked to, everybody, I'm talking about from my age to like 90 years old and older, say that yes, it wasn't quite as bad.
From
So,
isolation to
go ahead.
social media, I'm like from isolation to, I think most of the main problem is really just giving technology. Like everybody is too accessible, and because due to like technology and due to COVID being locked down for 2 years, people have lost the art of communication. Like everything's like, now you can just, instead of like sitting down writing a letter and having to think about what you say, because like once you send it you can't get it back, people can just text you and I send it. So it's like now people don't really have like that art of like being careful with their words and like knowing how to communicate. And then social media is also crazy. Digital blueprint. Someone can take a picture of your face and just put into this little app, and it can bring up every social media app that you're on. That's insane. Or like doxing, if you post like again your picture, just don't leave like a little too much information because someone could find your house, where you work at, your phone number. Like it's just too intrusive and invasive. It's gonna have to be a big reform, but astrologically speaking as well, for the next 20 years, because we're going to have Pluto just entered Aquarius. So for the next 20 years, it's going to be more evolutionary change amongst human and humanity, because Aquarius does rule the collective. So it's going to be a very interesting 20 years, and beauty will be a bigger thing now because Taurus is the kind of the thing that's going to hold everything together. So beauty is going to become a real currency again. So people should start investing in their looks like today.
Well, I do agree that it's definitely going to be a very interesting 20 years. And what I would offer is this, because it makes you feel like you don't have control, like that's also what brings fear, is feeling like you don't have control over your environment or your life. But all the things we talked about today, I will offer that. Again, I can't prove it. I haven't proven it. It's only speculated theory, but my personal experience leads me to believe that it's true and that it will be proven, or probably already has been, and just has not been put out in terms of conventional science. And it's this, the thing that you said earlier, Jamie. You do have control. Your thoughts can affect your environment in more ways than we actually realize, and maybe even in more efficient ways. So as opposed to trying to get out, I mean, these are ways to affect change in your environment. Protesting, debating, interacting. And that's good. I mean, we're social people beings, so it's good to be social. But that is not the only power that you have. Your thoughts, I believe, are much more powerful in affecting change, actual, real, quantifiable change in your physical reality than we realize. That is what quantum theory is suggesting. And if that's true, that is incredibly powerful. Probably the most powerful thing than what seems to be what we use as, in terms of tangible means of executing power and control. And so that can possibly give stability in a way if you know that, and you understand that, and you can project that on your reality. That actually is another dimension of power that most people don't even know. So maybe that's something to look into in terms of, and to maybe, lean into in terms of trying to establish and control and also influence what happens to our humanity and our species over the next 20 years. You don't just have to go around talking to people or arguing with people or whatever. You can also just go within yourself and project what you want. And the stronger that you can do that. And I'm possibly, as a scientist, I can't say that, yes, that's because I don't know. But, we move forward and we evolve based on our intuition and then, testing our intuition. That's how anything moves forward. And my intuition, based on my personal experience, tells me that all of this that I just laid out today is exactly how the universe is working. And but it remains to be seen. So I offer that, and sorry to let you take you over class. Over the discussion was very fruitful today. And yeah, this is quite interesting. It's quite fascinating. And yeah, that's why you're seeing all this stuff in these science fiction movies, because that is kind of an implicit information that is telling you that I'm not the only person thinking about this. These people are getting this from somewhere. They're just not making this up, right? So at least that's some sort of corroboration, at least implicit corroboration of what I've been discussing with you today. So yeah, thank you so much for participating, Jamie. I appreciate your questions, your comments, and your perspective. Anybody else want to add before we close our class?